SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, module number 2, Vapor Power System part 3. So, this is the last lecture of this module, and in which we will be concentrating on one of the important component of the steam power systems, that is cooling towers. So, before you start discussions on cooling towers, we will try to see basic background regarding various aspects of the power systems. First thing is the requirement of circulating water systems. So, here we will try to see that the main job of this cooling tower is to cater the needs of water requirement at various locations of the steam power systems. So, that is the reason we call this as a circulating water systems. So, there are different classifications to it. We will try to discuss them, like open through, once through mode, closed systems, closed mode, and combination mode. Then we will try to see the basic concept of the circulating water systems, that is the from the beginning when you start the concept of how to circulate the water at different components of the steam power systems. Then people started with various ideas such as cooling lakes, cooling ponds, dry cooling towers. So, these were the initial concepts for circulating water systems, but over the period of time the modern power systems use wet cooling towers. So, wet cooling towers, it takes the advantage of air plus water. So, main aspects of this cooling tower is to take out heat from during the condensation process. So, in the wet cooling tower we use combination of air and water and take the advantage of temperatures for water as well as air with the psychrometric concepts. And under this heading we will have a mechanical and a natural draft type. So, basic difference between these two is that in mechanical type we used different types of draft fans like forced draft fan, induced draft fan, whereas you take the advantage of height of the cooling tower or design the cooling tower for a large height to take the advantage of density difference of air, and that makes the circulation of air possible for a given local location and requirement. And one of the most important aspects of this wet cooling tower is basically the mass and energy balance equations that needs to be solved, but for that things we require the psychrometric terminology, and we will try to see that how that psychrometric terminology will help us in doing the various calculations for a wet cooling tower. This is the overall view of this cooling tower sections. Now, let us briefly talk about the need of the circulating systems. The first and foremost concept, if you recall our Carnot cycle and basic Rankine cycle, which means is that for a given power output from the turbine, we require heat addition in the boiler, we also require some pump work, and finally heat is rejected in the condenser. Now, heat rejection is a must, because based on the Carnot cycle concepts, when you say this is a heat engine which operates in a cycle, and this heat engine cycle is nothing but this particular thermal circuit of the steam power systems, and in which one of the way of heat rejection is the heat rejection in the condenser. Now, where is this heat rejection that goes out? it goes out to this cooling water. So, one of the important concept is that for certain mass of work output from the turbine, we must reject heat to the surroundings, and here the surrounding we mean either it can be air or the water which circulates in the condenser has to take out this heat. So, this is the basic need of the circulating water systems and mainly for condenser unit. Now, let us try to understand more basics of the Carnot cycle. So, if we just make some estimate considering this heat rejections from the Carnot cycle is QR, heat addition rate is Q dot A and work output is W dot with a cycle efficiency eta. Then if you look at for every case, let us say we are trying to get 100 megawatt of power with various efficiencies of the Carnot cycle. So, one thing you can notice here, for given work output, if you are by using these calculations with certain efficiency for given work output, if we can make a correlations how much heat we are rejecting to the surroundings or heat rejection rate, then we can say for 100 megawatt we have to reject about 400 megawatts for small old industrial unit. For fossil power units we must reject 300 megawatt and for nuclear power plant it is less, but whatever may be the case, we can see that heat rejection is a must, that is for the requirement of the Carnot cycle. But how much heat rejection, that depends on the nature of power plant that we study. Another important aspect is that we can say there is an improvement of 7% efficiency, that is from 0.25 to 0.33, which results 33% saving in heat rejection. And again our improvement of efficiency from 0.33 to 0.4, that results 25% of heat rejections. So, in very bottom line is that we must reject heat, and heat rejection quantity is about 4 times of the work output from the plant. At the same time, that means the requirement of cooling water is almost huge, maybe close to 4 times the amount of power which is going to be delivered from the plant unit. So, it is this huge requirement is for this huge requirement we must have a proper circulating water systems. Now, this circulating water systems normally is considered in variety of ways. First thing is this is once through mode. So, what does we mean in the once through mode is that the circulating water systems is based on 3 concepts. One is once through mode, closed systems and combination systems. Let us try to understand what is this once through mode circulating water systems. So, if you see this figure, we can see the condenser that takes in which exhaust from the plant comes from the turbine. So, this heat must be rejected to the cooling fluid. Now, here the cooling fluid can be the circulating water, and this circulating water can come from natural body of water, surface of the water. It may be a lake, it may be a pond, it may be a river. So, we can have a circulating pump that can enter, and this condensate again can be discharged back to this same river or same water bodies, but at a higher temperature. So, initial temperature is T1, but the final temperature is plus T1 plus R with some addition of heat, and again the condensate goes back. But here what we see is the heated water goes out to the again the same water bodies. Many times it poses ecological aspects of this water system of the river. So, that is the reason this particular method is not generally employed. So, we move on to closed mode. So, the closed mode means that you use a separate unit called as cooling tower that does all kinds of water treatment before it discharges to the water bodies. So, that is the reason. So, the closed mode circulating water system means first you take the water and send it to this cooling tower, treat it, then send it to the condenser. Again from the condenser you take back the hot water, again treat it, and finally discharge it to the water bodies. So, that way entire treatment is normally done in this cooling tower only, so that the ecological systems of river is not affected. So, this is what what I have explained so far. So, when you take the once through systems and discharge systems may be lake, river or ocean, and this discharge can be a surface discharge, submerged discharge or diffuser type of discharge. But there are various advantage and disadvantage of various methods, but most effective way is the diffuser discharge systems, in which we can send this control water, we can let the water out in a controlled manner through the nozzles operated in a long pipe, so that ecological aspects of water bodies remains unaffected. Again, this is a closed system mode. In the closed loop mode, the essential requirement is this cooling tower, which we will discuss more in details in the subsequent part. But here apart from this cooling tower options, the beginning options, that earlier options for heat disposal systems could be a spray pond or spray canals. So, there are other substitutes of cooling devices. Now, in a combination systems, what we do is it operates in both modes, like once through mode, or it can be operated through a closed mode. So, what it does is that, so the combination systems operates in a both modes, like once through mode or a closed mode. So, what we have extra devices here is there is a valve, and that valve operates in such a way that if the water has to be discharged directly to the water bodies, then this valve becomes operational. So, we run this system in a once through mode. If you want the water to be treated, then the valve has to be operated, that means entire water that comes out from the condenser goes directly to the cooling tower. After treatment, it again gets discharged. So, basically speaking, that in both the cases, if your initial temperature T1, which is takes from the water, and when you do it in a once through mode, the final temperature will be T1 plus R, and but when you do this combination mode, the final temperature is T1 plus TTD, and this TTD we call this as a terminal temperature difference, and that is nothing but the temperature at the exit of the cooling tower and the source temperatures. So, TTD is a very vital term, that is the difference between the exit temperature of the tower and the source temperature at which it is enters. And there is another term which is called as a range. Range is defined as the temperature rise across this condenser. So, we will discuss more details when you come back later when in our analysis of wet cooling tower. Now, let me give you some basic background, that in earlier systems, when there was no concept of wet cooling tower, then people starts using the concept of cooling lakes. It is nothing but their oldest and but simplest type of techniques for artificially rejection of heat from the steam power unit. So, what we normally do is that we can prepare an artificial made lake, that means we can prepare a area in which we put all the disposal of water into that lake, and in the lake we allow maximum residence time for this water, so that it becomes cool naturally. So, while cooling naturally, it can cool by evaporations or convection by wind or thermal radiation to the sky. So, through this means water gets cooled, and but what happens, but net effect of the cooling lake is not a constant, because over the lake area there could be variation of large water temperature differences and climatic conditions. So, ultimately for this kind of modeling, we come across expressions which normally gives equilibrium temperature of an cooling lake, which with a dependence from our heat transfer analysis we can do it, and that talks about this particular expressions, exponential expressions. In this, that is Tc minus Te divided by Th minus Te exponential to the power minus Ua by m dot C. So, here T is the equilibrium temperature, Tc and Th have the cold and hot water temperatures, C is the specific heat of water, mass flow rate of water is m dot, A stands for surface area of the lake, and we have one more term which is called overall heat transfer coefficient, and of course, we have another non-dimensional parameter, that is UA by m dot C, which is most frequently used in the heat exchangers for heat transfer analysis in the heat exchangers. So, this is what we say equilibrium temperature expressions for a cooling lake, and from there once you have this we can also find out what is the heat dissipation rate. The other concept is like a spray canals, which is also similar to a water cooling tower concepts. In this, what we have is the water is sprayed into air above this surface, and the flow pattern is such that it goes in a channel. Through this process, heat transfer takes place again by T2 evaporations, conduction of air, partial radiations. But another parameter that gets popped into here is that weather conditions, since air comes into picture here, air dry bulb temperature and wet bulb temperature is also needs to be considered. So, here we also use a similar governing equations, and the notations are given in these things. But however, this is just an introduction of this, but now in all modern steam power systems normally do not use these old concepts of spray canals or artificial pond. So, we normally choose direct method of using the circulating water systems through cooling towers. So, when you say cooling tower, there are two types, one is dry cooling tower, other is wet cooling towers. So, the first one is the dry cooling tower, in which you looking at this figure, we have the schematic. What it says is that the air and water, they do not mix each other, rather what we think is that the circulating water is passed through the fin tubes in which cooling air is passed. So, circulating water is passed through the tube and in which the cooling air is passed. So, heat rejections from the cooling water is in the form of sensible heating to the air. So, that thereby since we do not look into the concept of water vapor, so wet bulb temperature of air does not apply here. The term that is most important here is initial temperature difference. The next method is the wet cooling tower. In fact, wet cooling tower is a widely used methods, and in this wet cooling tower, the heat rejection or heat dissipation process has following mechanisms. First is addition of sensible heat to the air, that means air temperature increases when it takes the heat from the exhaust of the turbine. Then we take the advantage of evaporation of portion of heat to the circulating water itself, then addition of sensible heat of the natural water bodies. That means, we take the advantage of water bodies as well as increasing the temperatures. So, what we look at a wet cooling tower concept is that if you look at the figure here, the hot water inlet comes, which normally comes from the exhaust from the turbine, they are sprayed. Now, when they are sprayed, they are passed through a packing or fields. That means, it is just a kind of a arrangement where the entire slug of water gets splitted through series of nozzles, and they are allowed to spray through the packing or fill, and from the bottom air gets sucked through this packing. So, thereby when air gets in contact with this hot water, it absorbs heat, that means its temperature also increases, but again the air becomes, so water vapor concentration in this air keeps on increasing until it gets saturated. Once it is saturated, it cannot absorb further mixture, but what happens when it goes up, again when it comes in contact with water, its temperature goes up. So, thereby it keeps on soaking the water vapors from the hot water. So, thereby through this process, at the end of this outlet, we get the air which is almost heated and saturated. That means air doesn't have any more tendency to absorb any moistures from this water. So, through this concept that means we take the advantage of increasing the temperature of air. At the same time, the water vapor concentration in the air is also increased. So, thereby air has two temperatures right now, while at the starting point it has a dry bulb temperatures and it has certain wet bulb temperatures, but finally when it goes, air is completely saturated. That means both dry bulb and wet bulb temperature of the air becomes equal. So, through this process we take the advantage of air plus water vapor, in which we take all the advantage of heat rejection process from this hot water unit. Now, considering whatever I have explained, we have to look into the upper limit of this air outlet, and this upper limit of air outlet is nothing but the saturated air. Saturated air means air does not have any capability to absorb any more water vapors. So, evaporation of the cooling is stopped, and when such a things with saturated water, and that temperature we call this as a adiabatic saturation temperature or wet bulb temperature of the ambient air. So, this is the concept of the wet cooling tower system. Now, these wet cooling tower systems are classified by two ways. One is a mechanical draught type, draft or draught type, both are of same word, similar word. Other can be a natural draft or draught type, and when they operate in either form, they can be a counter flow type or a cross flow type. Now, let us understand what are these mechanical draught type cooling towers. So, here if you look at these figures, mechanical means you are artificially allowing the air to enter into the tower. So, there are two possibilities of air entry. Normally air enters from the bottom as shown in this figure. So, either it can be a forced draft type or induced draft type. So, in a forced draft type, we introduce a fan which is at the entry of the air inlet. So, thereby we are forcing the air to enter into this tower, and at the outlet the hot air goes on its own because it is already a hot air and its density is less. So, it goes naturally. But the main disadvantage in this process is that there is a tendency this fan introduces a back pressure, that due to this back pressure the air distribution issues in the film arises. There are possibility of leakages and recirculation of air back to the tower. That means air again after recirculation, again if there is sufficient pressure is not maintained, air again try to reverse back from towards this main inlet. So, that is the main disadvantage of a forced draft type cooling tower. But other options to remove these ambiguities is to consider this fan at the exit level. So, when there is a outlet, at the outlet level you use a fan, and that fan is nothing but induced draft type. So, it is basically you suck the air, whatever it is coming, you create a pressure difference in between. That means entire things pressure difference is felt in the entire tower, so that by virtue of the pressure the air gets sucked in from the bottom, and there is hot air goes out at the outlet, and through this process there is other advantage that happens is that mixing of water with air is very much possible in this field or packing. That is an most important advantage for a induced draft type tower. Second thing, issue of back pressure does not arise. So, because of this advantage, most of the wet cooling towers are normally induced draft type, and if it of course if it is a mechanical draught cooling tower. But main advantage is low capital cost, construction cost, small physical structures, of course assured supply of quantity of air at all loads and all climatic conditions. The other way or other concept of wet cooling tower is to consider a natural draft type. So, basically the issue of fan is induced, either induced draft or forced draft is not does not apply here. So, what you take the advantage? To take the advantage of this driving pressure as a density difference. So, in other words, you say you use the concept of rising a height of the, that means you increase the height of the tower in a manner such that in a tall tower we can get the advantage of density difference of atmospheric air and within the pressure inside this cooling tower. So, driving pressure becomes the density difference type G tends to H. So, essentially the height H is nothing but height which is just above this field. So, of course, this is the empty space, but this empty space is required to maintain this density difference. In that way, we take the advantage of the atmospheric air and air inside this cooling tower to create this density difference. In fact, this natural drought type cooling towers has huge structures, and the tower body above this water distribution systems, which is somewhere here, is an empty shell of circular cross sections, but with hyperbolic vertical profile. So, in the vertical profile it is hyperbolic, and that this structure is mostly preferred, and they are made out of reinforced concrete, and because it gives superior strength, greater resistance to the unit loading at as compared to any other configurations. And moreover, if you want to see the difference between the mechanical draft and natural draft cooling tower, the essence of using a natural draft cooling tower is that they are suited for cool and humid climates for which we have low WBT, that means low wet bulb temperature, and high relative humidity. When we have advantage of having low WBT and high condenser water inlet and outlet temperatures, when there is a heavy winter loads, that means in a winter environment or in the cooling areas where we have this kind of climatic conditions, then the choice of natural cooling tower is taken into account. But for other places, mostly mechanical draft type and that uses induced draft fan are mostly preferred. The another approach of design for wet cooling towers is to take into consideration of the parameters what we call as approach and range. For example, mechanical draft cooling towers use low approach and broad range of water flow, whereas natural draft types are preferred for long approach and broad range of water flow. Okay. Now, till this point of time, we have seen all types of cooling towers, but most preferred cooling towers is a wet cooling towers, and here we will try to understand how the heat is taken by the circulating water systems as well as from the air. So, for that viewpoint, we require the knowledge of psychrometrics, and we will try to understand how this psychrometric analysis or terminologies help us in framing the governing equations. Essentially, the wet cooling tower calculations involve mass and energy balance based on the steady flow and steady state equations. And there are three fluids which are involved here. One is cooling water, second is dry air, and third is water vapors, and water vapors which is associated with this dry air. In addition to this, there is also a term humidity which is plays very important role, and other assumption what we say that water vapors in the air is always at a very low pressures. So, we treat them as a gas mixture. So, instead of water vapor, we use it as a ideal gas mixtures, in which we can use this ideal gas model for this analysis of water vapors. So, there is a term which is called a saturated air. Saturated air is a condition of air in which the air cannot accept any more water vapors at a given temperatures. So, this can be obtained from the data tables in the steam table. That means, we all know that for every saturation temperatures and there is a saturation pressure and vice versa. Any drop in temperature in the saturated air will lead to condensations. So, a newer cooling air would also be saturated. An increase in the temperature of the saturated air would make it unsaturated, that means it can accept more water vapors. That means once it is condenses, it cannot accept any more water vapor. That means I have to add new air into it. But if you want to increase the, any increase in the temperature of the saturated air will make it unsaturated. So that way we can accept more water vapors. So that is the controlling parameter that we can have in this wet cooling tower concepts. So we take the advantage of this and keep analysis and do our analysis. And all our conditions, we will take the pressure saturated condition as 15 degrees, total pressure as 1.01325 bar, based on which the psychrometric calculations are normally done. At that temperature, you will from the steam table you will find the partial pressure of water vapors. So that way we can also find the partial pressure of dry air, which is the difference between these two. The other term, which is called as a relative humidity. So relative humidity is equal to the ratio of partial pressure of water vapor in the air to the partial pressure of water vapor that would saturate the air at that same temperatures. So this is a non-dimensional term. Then we have absolute humidity, humidity ratio or specific humidity, they are all same term, and it is the ratio of mass of the water vapor in the air to the mass of the dry air. So the saturation pressure increases rapidly with temperature at all vapor pressures. So the warm air can hold more moisture than the cool air. That means when your temperature increase, it can hold more moisture. The other term is called as a degree of saturation. So it is the ratio of actual specific humidity to the saturated specific humidity. So again it is a non-dimensional term. Now for air we have three temperatures. One is called as dry bulb temperatures, other is wet bulb temperature, third is dew point temperatures. So if you recall this temperature entropy diagram, property tables for water, at any locations if you locate the state and whatever temperature you call, that is a dry bulb temperature. Now what you do, you try to measure the temperature of air by putting this bulb of this thermometer, keeping it wet. So that way the temperature recorded by the thermometer would be less than this dry bulb temperatures. So essentially, so we are going along a particular constant pressure line and we are reaching one locations which will be at WBT temperatures. Now by putting this dry bulb temperature, if you keep on cooling the air and we will reach at the saturation curve, and that point the air is no longer able to accept any more moistures. That means air is going to condense. So water vapor in the air is going to condense. So we call this temperature as dew point temperature of air. So psychrometric term has three temperature: dry bulb temperature, wet bulb temperature and dew point temperatures. So this is what we have explained here. Main important aspect in this cooling tower analysis is the wet bulb temperatures. If the air is relatively dry, water would evaporate from the gauge at the rapid rate, resulting the cooling of the bulb. So we record this as a wet bulb temperature. If the air is humid, evaporation rate will be slow. So that means wet bulb temperature approaches to dry bulb temperatures. We also call this wet bulb temperature as adiabatic saturation temperatures. Then dew point temperature means at the point at which the water vapor in the air begins to condense. So it is this equilibrium or saturation temperature corresponding to that partial pressures. And for a saturated air, all the temperatures, that is DBT, WBT and dew point temperatures are all equal. So whatever you have discussed so far, a complete analysis of psychrometric terminology we can define by these expressions. So here relative humidity, ratio of partial pressure of water vapor to the saturated pressure, then specific humidity, which is mass of the water vapor to the mass of dry air, and considering these ideal gas assumptions for water vapors, we can write down these gas equations, that is for water vapors and for dry air separately. So based on this we can get the expression for specific humidity in terms of pressure of water vapors to the pressure of dry air. Then we can obtain the expression of degree of saturation, that is omega by omega max, and this omega max is obtained by putting the PV is equal to PS. So, that is the maximum specific humidity that we can obtain. Now, with this psychrometric term, we are now able to analyze the concept of psychrometric analysis. So, here there are three fluids, one is cooling water, dry air and water vapors in the dry airs. So, you take a model which you call as a steady state steady flow model for a cooling tower, in which there is a hot water entry and cold water out, again cold air entry and hot air out. And when you say air, it has two parts, one is dry air part for which enthalpy is HA1 and the enthalpy for water vapor is represented as Hg1, corresponding its omega 1. Similarly, for hot air out we have HA2, omega 2 and Hg2. So, we take the advantage of the difference in the specific humidity of air, which absorbs more and more moisture as it passes within this tower. So, now if you see the complete equations for the energy balance for a cooling tower with this concept, then you can frame these energy balance equations. So, energy balance at the inlet we can have HA1 plus omega 1 HB1, and for water inlet we have WA into HWA. So, W stands for mass of the circulating water per unit mass of dry air, and then again on the outlet side we have air outlet and water outlet. So, WB, HWB, and in of course here HW stands for water because it is a hot water and cold water, but their temperatures are different. Then for air, which is at 2, and at 2 it is almost saturated, air is almost saturated. Okay. So, considering this, most of this data for given problem, most of this data can be obtained from the steam tables and using these equations. The other approximations when you do this for air analysis, the enthalpy difference for, because this air which have a dry part, other part is water vapor. Now, difference between HA1 and HA2 is associated with this difference, that is Cp times T2 minus T1. So, once you know this inlet and exit condition of air, we can find the enthalpy difference for air. So, air and water vapors has to be treated differently. Now, putting these equations, our final expression, and of course, the mass balance equations, it is nothing but dry air mass remains unchanged, only the difference between the specific humidity will give you the difference between the whatever water vapor gets added into this air. So, this is about the final equations for energy balance and which talks about in this form, and this is nothing but your working equation for solving the problem. So, you must remember this. Another part of this cooling tower design that we also expect a pressure difference. So, the pressure difference normally is achieved from the outside air whose density is rho 0 and from the inside air whose density is rho I. And this rho 0 and rho I has two components, one is dry air, other is for vapor. So, it is treated in a differently, density calculation is treated in a differently. Firstly, we take the calculation for water vapors. First part consists of for air, dry air part, second part consists of water vapors. That means, this is for outside air. Similar way we can have the density difference for the inside air, and this entire analysis will give you this density difference that occurs between the outside air and the inside air, and this density difference with having this height will give you the driving pressure for a natural draught type cooling tower. So, this is all about the entire analysis for void cooling towers. So, with this analysis, let me frame this particular problem with some numerical data. So, whatever analysis we have done so far, we are now going to use this for this numerical problems with appropriate data for a specific case, which is a natural drought type cooling tower. So, the problem statement as this, you recall our schematic model in which we have hot water in, cold water out, cold air in, hot air out. So, from this figure and data, if I write down different conditions, so let us see what is the hot air in. So, hot air in is whatever data is given, which is W dot A 360000 gallons per minute. So, if you simplify to kg per minute, we say W dot A becomes 22714 kg per minute. And what is temperature of water which enters 32 degree centigrades. Okay. So, at these temp conditions we can find out what is HFA from this steam table. So, this number is 134.14 kilojoule per kg. Then hot water out. So, we have WB, which is nothing but WA minus the omega 2 minus omega 1, which is the amount of water vapor which gets absorbed by the air. This is per kg of dry air. And temperature at the outlet TB is equal to 21 degree centigrade, because we have range is 11. Range means that is TA minus TB is equal to 11 degree centigrades. So, TA 32 means TB will be 21 degree. Okay. So, this is for water part. Now, let us consider air part. So, air condition is T1, temperature of outside air is 15 degree centigrade, pressure 1.01325 bar, relative humidity phi1 is 50%. Then at this temperature we can find out what is PV1. This is 0.008525 bar. Then at saturated pressure is 0.01705 bar. Because we have phi, we can take phi as PV 1 by PS, PV by PS1. So, phi is given here. Okay. PS1 we can get from T1 using steam table. So, that is 50%. So, this one will give you PV1. Then further information we can calculate omega 1 like 0.622 PV1 divided by P minus PV1, and from this we can calculate omega 1 is equal to 0.005277 kg by kg dry air. Once you know this, then at temperature T1 15 degree centigrade, steam table will implies Hg1, that is vapor. You have to use the vapor condition 2258.9 kilojoule per kg. So, all the parameters known, and HA1 is Cp times T1. In similar way, hot air out. So, hot air out is saturated. Exit condition of air is saturated, that is T2 is equal to 27 degree centigrade. So, we can say what is PS2 0.03567 bar, and then PS1 is that omega 2 would be 0.02268. Total pressure remains same, So we have omega 2, then we have Hg2 corresponding to 27 degrees centigrade using steam table. It is 2550.8 kilojoule per kg. Then Ha2 is equal to Cp times T2. So we have at all locations, we have all the data. Then we can use our working equation, which says that W1 omega 1 Hg1 plus WA HFA is equal to here also HFB. HFB would be 88.14 kilojoule per kg is equal to Cp times T2 minus T1 plus omega 2 Hg2 plus WA minus omega 2 minus omega 1 multiplied by HFB. So in these equations we have all the data, that is 0.005277 into Hg1 is 2258.9, WA is unknown, HFA is 134.15 is equal to 1.005, T2 minus T1 is 27 minus 15 plus omega 2 is 0.02268, Hg2 is 2550.8 plus WA minus omega 2 minus omega 1, that is 0.02268 minus 0.005277 entire multiplied by 88.14. So this equation can be solved for WA is equal to 1.23 kg by kg dry air. Okay, so but our question was what is the makeup water. So moving further, so from this we can find out what is the amount of dry air requirement, which is m dot A is equal to W dot A by WA. So W dot A is already you have calculated, gallons per minute to kg per second, 22712.4 divided by 1.23. So this should be 18465 kg per second, or m dot A becomes equal to 1.1 into 10 to the power 6 kg per second. So first part of this and things we can write what is the makeup water. M dot makeup would be m dot air into omega 2 minus omega 1. So that is 1.1 into 10 to the power 6 into 0.00268 minus 0.005277. So makeup water requirement becomes 19143.3 kg per minute. Then we have this second part is the volume of the flow of water. So volume flow rate of outside air. So for that we need to find out density of outside air, P minus PV1 divided by RA T1 plus PV1 by RV T1. Inside air, P minus PV2 by RA T2 plus PV2 divided by RV into T2. So, RA we can find out 8314 divided by its molecular weight 28.96, 287 joule per kg Kelvin. RV is equal to 8314 divided by 18. This is 517.4 joule per kg Kelvin. So, from this with all the data we can get rho I is O outside air density 1.22 kg per meter cube, rho I is 1.203 kg per meter cube. Then volume flow rate, outside air requirement would be m dot A into 1 plus omega, that is equal to 1.0 omega 1. Omega 1 data is already there, 1.1 into 10 to the power 6 into 1 plus 0.005277. M dot out is 1.105 into 10 to the power 6 kg per minute. So, okay, this will be kg per minute. So, out then volume flow rate would be m dot air outside air divided by its density, outside air density. So, this number will be 0.9 into 10 to the power 6 meter cube per minute. The second part analysis is done, that is what is the volume flow rate of outside air. And for third part we have this pressure difference, that is delta PD is equal to rho 0 minus rho I into G times H. So, your height is this H, delta PD is given 72.5 Newton per meter square, G is 9.81 meter per second square. So, and density difference rho 0 and rho I are known. So, this will give you H is equal to 435 meter. So, for a natural draught cooling tower with this data we require a height of 435 meter for continuous operation of air to maintain this density difference. So, it is a huge structure normally done in the reinforced concrete. So, this is all about the numerical problem associated with this wet cooling tower. So, with this I conclude this lecture, and with this the module 2 is closed, and thank you for your attention.